Hello everyone, welcome to my presentation. I am Anshul Pagwar and I am going to present my work on Frustum Pointpillars, a multi-stage approach for 3D object detection using RGB camera and LiDAR. I'm really sorry for my voice today. I have a bad throat from past few days. So let's dive into this presentation. I will start with introduction about the 3D object detection. Then we'll discuss the difficulties with pedestrian detection and discuss more about the different sensor fusion approaches using RGB and LiDAR. Then we will see our method, finally some results and conclusions. 3D understanding of the environment is vital for many applications for autonomous driving, and LiDARs are one of the most widely used sensors in autonomous vehicle as they are very robust to varying environmental conditions. But the problem with the LiDAR is that they generate point clouds, sparse and unstructured, and it is more challenging to extract relevant features from this kind of a data set. Nevertheless, significant progress have been made in learning features directly from raw point cloud. A breakthrough approach is PointNet. Then many other 3D object detection methods use PointNet as a main feature extractor, for example, VoxelNet and Pointpillars. So Pointpillars proposed a method to divide the large point cloud from the autonomous vehicle into a 2D grid of pillars and then use PointNet within each pillars to extract pillar feature nets. This significantly improves the runtime and also the accuracy. So these 3D detection approaches using LiDAR only data perform good for large objects like cars and vans, but they suffer at localizing smaller objects like pedestrians. One of the main reasons behind this is that the point perturbations of pedestrians do not have a distinctive geometry structures and have a very few data points. For example, on the right, you can see the image. There's a point cloud of a pole versus a pedestrian. It is very difficult to distinguish between these two. But with the RGB image, you can distinguish pedestrians very clearly. Also, another difficulty is that unlike cars and vans, the pedestrians are not a rigid bodies and they can deform their structures. For example, this pedestrian when walking can look similar to like this. On the bottom here, we can see we have a current state of the art for pedestrian detection in RGB and point cloud, and we can clearly see that the 3D detection is lagging significantly. So we propose to use some sensor fusion approach that leverage mature RGB detection rather than solely relying on point clouds for 3D detection. So we classify sensor fusion approach in 3 different categories. First is early fusion, late fusion, and multi-stage approaches. Out of these 3 methods, multi-stage approaches have for sensor fusion have shown a high accuracy for pedestrian and cyclist detection in 3D. So we build our network upon this multi-stage approach. So the key idea behind the multi-stage approach are that is to use different sensor modalities according to their strengths. For example, RGB cameras for 2D detections and LiDAR for 3D localization. Given the 2D detections of the objects in the scene, these approaches extrude the 2D detections into a 3D bounding frustum, and the points outside the frustum areas are removed, thus reducing the search space in the point cloud. 2 of the most popular approach using multi-stage method is Frustum PointNet and Frustum ComNet. So Frustum PointNet use PointNet with all the points within the frustum to find a model 3D bounding box, whereas Frustum ComNet discretize this bigger frustum into more smaller frustums and then uses PointNet within each frustum, finally finding a 3D bounding box. Our proposition in this work is to take a step further and discretize this 3D frustum into much finer grid of 2D pillars so that we can extract features at a much higher resolution. So the proposed method of Frustum point pillars extends the architecture of point pillars by addition of RGB camera and use the multi-stage approach. We also extend the data augmentation for training to work with multi-stage network architecture. But one of the key contribution is a simple but efficient Gaussian-based masking of 3D point clouds to distinguish foreground from background clutter. This significantly improves the localization of objects in 3D. The key idea here is that within 2D region proposals, objects of interest is most likely to be in the center. So for each 2D detection, a mask is created using a Gaussian function representing the likelihood that the pixel belongs to the object. These likelihood values are then projected onto the point cloud as shown over here. After filtering and masking process, we use Pointpillars architecture as our backbone to regress 3D bounding box. We trained and evaluated our method on a Kitty 3D object detection dataset, and after submission to the Kitty server, our method is ranked 28 for pedestrian detection. Our method outperforms Pointpillars and Frustum PointNet and Frustum ConNet on the hard difficulty level, whereas for the bird eye view detection, we outperform all these three approaches on all the difficulty level. So for bird eye view detection, currently we are the state of the art on Kitty dataset. Also, our network achieves significantly better runtime of 14 Hz than the other state-of-the-art approaches. We perform different experiments and ablation studies using Kitty validation dataset to better understand the performance of different components of our network. First, we test how using a Frustum-based approach and Gaussian mask affect the performance. As it can see from the table 2 and table 3, using the Frustum-based approach improves performance up to 4 to 7% across different object categories. And then using a Gaussian masking adds another 2 to 3% of improvement. Here are some illustrations of different diverse scenes from Kitty dataset. So images shows 2D region proposals from an off-the-shelf 2D detector. This is the Gaussian mask on top of it. This Gaussian mask is projected onto the 3D point cloud. And then finally, you can see the output from our network 3D bounding boxes. For the conclusion, we propose Frustum Pointpillars, a multi-stage design approach that uses both RGB and LiDAR data for 3D detection. We also propose a novel approach for masking 3D point clouds with the likelihood values to distinguish foreground from background clutter. Frustum Pointpillars outperform other multi-stage approaches for 3D pedestrian detection in hard difficulty level and bird eye view detection in all difficulty levels. Our method achieves a runtime of 14 Hz and is significantly faster than other multi-sensor approaches. As for the future work, we would further like to improve our runtime by using sparse convolutions in the backbone of our network. Again, we would like to leverage this object class information we get from the 2D detector to improve multiclass 3D detection. Finally, here are some references, and thanks a lot for listening to my talk. And if you have any questions, I'm welcome to answer your questions.